These are the notes from Monday, November 30th, geometry class. We're going to look at two theorems and their converses today. The first one is the perpendicular bisector theorem. I want to get a couple definitions out of the way before we look at the theorem, though. First of all, if you remember, we've had the word bisect before, and what that means is to cut something into two equal pieces. So a bisector would be a line or a segment that cuts something into two equal pieces. Since we're looking at perpendicular bisector, we're going to look at a line that is perpendicular to another line and that also cuts that second line segment into two equal parts. Another word that I'll use is the word equidistant. Part of that word is equi, E-Q-U-I, which means equal. Distant, obviously, is the distance. So when something is equidistant, or a point is equidistant from two things, it means it is the same distance. The sentence that I have there is when a point is the same distance from two or more objects, the point is said to be equidistant from those objects. So that's a word that I'm going to use, and it's going to be used in the theorem. Okay, so let's look at the perpendicular bisector theorem. I want you to look at the picture as I read the theorem to you, and I will point out the parts of the picture that I'm talking about. First of all, it says, if a point is on the perpendicular bisector of a segment. So the point we're talking about is the point X up here at the top. So that's the point we're looking at. And the perpendicular bisector is the line L that's running up and down. It is perpendicular to AB. You can see the little red square there, meaning that it's perpendicular or meets at a right angle. And bisector, we can tell that it's the bisector by the little red hash marks on either side. It's saying that the distance from Y to A is equal to the distance from Y to B. All right, so my line L, which is running up and down, is perpendicular to AB, and it also cuts AB into two equal parts. If you'll take a look at the statements that are underneath the picture, that is what those two statements say. XY, that segment is perpendicular to segment AB, and segment YA is congruent to segment YB, which means they have the same length. Okay, that is the hypothesis. All of that is the hypothesis in our statement. The second part of the theorem says, then it, meaning X, is equidistant from the endpoints of the segment. So that means X is the same distance from A as it is from B. So the two lines that are line segments that are in red are also equal. So if we look at it all together, okay, since X is on the perpendicular bisector of the segment AB, that means it is also the same distance from point A as it is from point B. And we're going to use that here in a minute in a couple of examples. The converse of that statement is also true. If you remember what a converse means that the hypothesis and conclusion are exchanged. So the converse says that if our point, that's X, is the same distance from A as it is from B, it's equidistant from the endpoints of a segment, and A and B are the endpoints of the segment, then it must be on the perpendicular bisector of the segment. So the conclusion is that XY is perpendicular to AB, and that the two short pieces down there at the bottom are the same length, or in other words, XY cuts AB into two equal parts. So the original theorem and its converse are both true. All right, so let's take a look at how we can use those. We'll apply them. Let me see if I can make them, try to keep the theorem at least where you can see it. All right, so let's look at example 1. I have a triangle there. From the picture, you can see that line L is perpendicular to segment XY, and it also cuts XY into 2 equal pieces. So in other words, it is the perpendicular bisector. Line L is the perpendicular bisector of XY because it's perpendicular to XY and it bisects XY. L bisects XY. So by our theorem, that means that, or that implies that, YW and XW are exactly the same length. So if we know that XW is 7.3, then that means that YW is also 7.3. And that is using that perpendicular bisector theorem just exactly like it's stated. Okay, I'll let you think about that one a little bit, and let's take a look at another picture. All right, the second one. This time I've turned that triangle on its side. I don't want you to get too used to looking at them always standing up on that one side that gets bisected. All right, so this time we have triangle ABC, and we can see that L is perpendicular to BC. We're given that, because we can see that by the little red mark. And if you look at all the measurements, we're also given that AB, that segment, has the same length as AC. Well, if you go back and look at the converse theorem, it says if a point is equidistant from the endpoints of the segment. Well, point A is equidistant from B and from C. We also see that it's on the perpendicular because of the red mark. Then by the converse, it is on the perpendicular bisector of that segment. So by the converse theorem, what we know is that L bisects BC, that segment. Well, if it cuts it in half, and half of it is 16, that means that BC is twice that, 2 times 16, or it has a length of 32 units. Because half of it is 16, that means BD would also be 16, so 2/16 would be 32. All right, one last one. We've used the theorem, we've used its converse. Let's see what this next one brings. All right, another triangle sitting on point R. And if you look at the picture, SR is perpendicular to PQ. It also bisects it, so what we're looking at is that line SR is the perpendicular bisector of PQ. So by the theorem, PR and QR are of equal measure. So if we could figure out one of them, we'll know both of them. And we're looking for PR. We don't have any numbers, but we do know that PR is 2n plus 9. We know that QR is 7n minus 18. And if you look at the equation, since they're the same length, we can set them equal to each other. If we could find n, then we could solve for PR. So let's solve this thing for n. I'm going to subtract the 2n from both sides of that equation. We get 9 equals 5n minus 18. If we add the 18 to both sides, I'll get 27 equals 5n. And then divide both sides by 5. This isn't going to come out even, so I could leave it as 27/5. Or if I go ahead and divide it out, I will get 5.4 for my n. So since PR is 2 times n, it's 5.4 plus 9. That would be 10.8 plus 9, or 19.8 is my length of PR. I don't know the exact units, so it's just 19.8 units. All right, so out of the 3 examples, we had the first one and the last one. Use the fact that we had our point was on the perpendicular bisector, so the 2 slanted sides of that triangle were the same. And then your second example used the converse theorem. Since we knew the 2 slanted sides of the triangle were equal, then we knew it was on the perpendicular bisector. That should help you with some of the problems I'm going to ask you to do.